Hello everyone, I am Dr. Osman and this video is a short extension to the previous video, and we will look at the comparison between species balancing and atomic or element balancing. So we'll just look at some cases and examples where atomic balancing would be preferable to species balancing and vice versa. Okay, so let's begin. If we look at the previous example more carefully, we can note that in the case of our balances for the gasifier, it turns out that we could have actually solved the gasifier balances by using the method of species balances rather than element balances. And it would most likely have been easier than having to write up these element balances in this fashion. So the question is, when will species balances be more advantageous, and when will element balances be the more preferred option? So let's look at the advantages and disadvantages of species and element balances. In the case of element balances, the advantage is that usually with element balances we end up having to write less balances. Okay, so typically in systems or processes where we have a large number of species, however they are only made up of a handful of elements, so we can write out fewer balances. This can be a good thing or a bad thing. If it's good, it's good in a way that our calculations will be simpler. We have less balances to work with. However, it could be bad for the process because it means that when we have less balances, then solving the problem becomes more dependent on subsidiary relations as well as specifications. The disadvantage of element balances is that the solution often requires a simultaneous approach rather than a sequential approach. So we end up with some complicated balances, and we typically have to put it in a matrix, and it's difficult to reduce that matrix, especially if we are working by hand. And also we have the additional task of needing to check the independence of element balances. We can't simply write out all of our element balances like we can for species balances. Now in the case of species balances, the advantage is that our solutions often have a sequential approach to solving the problem rather than a simultaneous approach. However, the disadvantage is that we could end up with many balance equations to work with. From a calculation point of view, it's a disadvantage because of course the calculations will be more complex. However, many balance equations can be good for the process because it means that we will need less specifications and subsidiary relations. And also a disadvantage, particularly in the case of reacting systems, is that if we want to use species balances, then we need to check reaction independence. So those are the advantages and disadvantages. But how do we make a choice? Now, when reactions are unknown or when species are unknown, then element balances are the only option. Okay, if we don't know what our reactions are and what our outputs are, it's impossible to do a species balance calculation. We would have to resort to element balancing. But for non-reacting systems, or for reacting systems where the reactions are known, we could choose between element or species balances. Let's look at a rigorous approach on how to make that decision. Okay, and let's look at our equations once again for non-reacting systems. In the case of element balances, we have the following relationship, which is true. The net output rate of each species multiplied by the number of elements will ultimately equal to 0. Okay, so at steady state, our elements are conserved. So this relationship is true for I going from 1 to E for E elements. In the case of species balances, our net output flow rate of each species is 0. Remember, this is a non-reacting system, so this relationship is true. And also note that all species balances are automatically independent, but not all of the element balances may be independent. We have to check for independence. So let's let rho of alpha equal to the number of independent element balances and S be the number of species that we are considering. If rho of alpha is equal to the number of species, the number of element balances is equal to the number of species, then it doesn't really matter which approach you use. Okay, each calculation method will be of similar complexity. However, if the number of independent element balances is less than the number of species, then species balances are actually more preferred. Okay, and this is because it implies that with a larger number of species, we will have more balance equations and hence less dependence on subsidiary relations and a more likelihood of solving the problem. What about the case of the number of independent element balances being greater than the number of species? Well, I can tell you that there will never be such a thing. Even if we have a process where there are more elements than species, the actual element balances will not all be independent. So even if we have a larger number of elements than species, the independent element balances will still be very low. Now let's look at reacting systems. Okay, so let's consider a system with V stream variables, S species, and the stoichiometry of the reactions are known. There will of course be S independent species balances and rho of sigma independent reactions. So the total number of variables is ultimately the number of stream variables plus the number of independent reactions. Okay, we've gone through this before. And a simple calculation is that the degree of freedom in the case of species balances is equal to the number of stream variables plus the number of independent reactions minus the number of species, in other words, the number of species balances. So this is our degree of freedom, neglecting, of course, our specifications and subsidiary relations. Now, in the case of element balances, we don't need to worry about the number of independent reactions. However, we will have rho of alpha of independent element balances. And our degree of freedom in the case of element balancing is equal to the number of stream variables minus the number of independent element balances. Now, if we can perform the calculation and determine our degree of freedom for each of the types of calculations, we can make deductions. Okay, so in the case of the degree of freedom for species balances being equal to the degree of freedom for element balances, we can, of course, have this following relationship, and by rearranging, we get the following. Okay, by cancelling the number of stream variables, we end up with rho of sigma being equal to the number of species minus the number of element balances. Okay, and so this is ultimately what we are saying. The number of independent reactions is equal to the number of species balances minus the number of independent element balances. And it turns out that if rho of sigma is less than the right hand side of this equation, then it is preferable to use species balances. However, if it is greater, the number of independent reactions is greater than the difference between the number of species, and the number of independent element balances, then it is preferable to use element balances. Now let's look at an example in this regard. Okay, so in the production of nitric acid from ammonia, okay, we have the following coming in: N2O4, NO2, as well as nitrogen coming in at stream 2 and water coming in at stream 1. And we have our two output streams where we have our nitric acid coming out in stream 4. And we are being given some subsidiary relations here. Okay, the following subsidiary relation, as well as a summation N2O4 plus NO2 is equal to 6% in composition. And we have the following ratios. In this example, we are also given the actual reaction, so we know the stoichiometry. So it is possible to utilize species balancing or element balancing to solve this problem. So the question is, which is more suitable to find a unique solution? To answer this, we need to find all of our terms in this particular equation. Okay, so we need to find the number of independent reactions, the number of species, and the number of independent element balances. Finding the number of species is quite easy. We can just count them. Okay, so we have 1, 2, 3, 4, 5, 6, 7. Okay, so there are 7 different types of species associated with this reactive absorber. So our S is equal to 7. Now we need to find the number of independent reactions, and we do this as before. We know what our reactions are. We simply need to reduce them. So we put them in a matrix. Here's reaction 1, 2, and 3, and of course all of our species. And by performing our Gaussian reduction, we see that none of our reactions disappear. So rho of sigma is equal to 3. Now we need to find rho of alpha, or the number of independent element balances. And we've looked at this as well. There are 3 different elements and of course 7 species, and we can list all of their element counts in each species and perform a rho reduction. And we note that even with a rho reduction, we still have 3 independent element balances. So we have rho of sigma being equal to 3, which is the left hand side of this equation here. And we have our number of species minus our number of element balances being equal to 4. Okay, 7 minus 3 is 4. So 3 is less than 4, of course. And by our criteria, it appears that in this particular case, it's preferential to use species balances to obtain a unique solution. Okay, so this implies that if we use species balances, we will have less dependence on our subsidiary relations and composition and flow specifications than if we used element balancing. Okay, and that is the issue resolved.